Thank you. Good morning, Professor. Good afternoon, professors. So I'm Dorothy Cheng Wai-Chung from Diocesan Girls School, and today my topic is going to be a geometric approach to the second non-trivial case of the Erdos-Gitters conjecture. So first I want to apologize because I just had a biology exam today morning. I will have one tomorrow, so my mind is not exactly on mathematics, so if I forget what I say, please forgive me. Okay, so the conjecture is basically for every set of 2 to the power n minus 2 plus 1 points in general position on a plane, there's a subset of n points that form a convex n-gon. And I really like this problem because it's simple and elegant, and well, math is simple and beautiful because it's simple and elegant. So let me talk about some known results. The specific ones are f3 equals to 3. F is the lowest number of points in general position to guarantee that there is a convex n-gon. So F3 is equals to 3, which is trivial. F4 is 5. It's called the happy ending problem, proved by Esther Klein. F5 is equal to 9. It's actually really special because there are two different proofs published for this, one in 1970s and one in 1974. And F6 is equal to 17 by Skeeters and Peters in 2006. It's a computer proof, and apparently this Skeeters man devoted his whole life to doing this. Okay, so the general results, the lower bound is 2 to the power n minus 2, meaning that there are some constructions with 2 to the power minus 2 points which does not have the convex n-gon, proved by, well, the two original proposers in 1961. And the newest upper bound is 2 to the power, well, n plus 4, n to the power 4 over 5, proved by Andrew Sook from MIT in 2016. This year. It's in the April. I was pretty surprised when I saw this because, well, it's a pretty new proof to be in this year. Okay, so this problem is a combinatorial geometry problem, and almost all proofs are based on combinatorics and coordinate geometry, including the proof of the lower bound, the proof of F6, the computational proof, and the proof of the newest upper bound. So they all considered like caps and cups and coordinates and also different combinations. And I was thinking maybe geometrical approaches or purely geometrical approaches may bring new perspectives to the problem. Actually, I was inspired when I was looking through Andrew Sook's proof in 2016 because there were some very geometrical diagrams in it. So I was thinking whether I can do something about it. So my project is that I proved F5 equal to 9 again using a purely geometrical approach, which is, I originally was more ambitious. I wanted to do F6 equals 17 or even more, but then I ran out of time. So terms and notations. The XYZ configuration is the convex hull organization of a defined set of points. So for example, the 3-4-2 configuration means that there's a convex hull of 3 points, of 9 points, and then inside the 3 points there is another subconvex hull of 4 points, and inside the 4 points there are 2 points. And Fn is the smallest number of general position required to guarantee the existence of a convex n-gon. Okay, so here are a few theorems that form the basis of my proof. Among any 5 points in the general position, there exist 4 points which form a convex quadrilateral, the happy ending problem, which is proved. The next one. Among any 4-1 configuration, means that 4 points of a convex hull surrounding 1 point, the middle 1 point will form exactly 2 convex quadrilaterals with 3 of the 4 points outside. So in this case, E would form a convex quadrilateral with ACD and, on the other hand, ABD. So there are exactly 2. The proof is pretty simple. You just draw a diagonal, and whichever triangle that point is not in, there would be a convex quadrilateral because it's limited by the angle sizes. Okay, so lemma 3.1.3, it says that for every 2 points for every 4-2 configuration, we will be able to divide the outer 4 points into 2 groups of 2 points, such that these groups do not form a diagonal. For example, in this case, it would be either AB and CD or AD and BC, such that the middle 2 points would form a convex quadrilateral with the outer both of the pairs of points outside. The proof is also pretty simple. For example, we first consider a 4-1 configuration with A, B, C, D, and E in the middle. And we divide this A, B, C, D into 8 parts like this. So first of all, we suppose that there are no convex pentagons. Because if there are convex pentagons, then, well, we're done with the problem. So we can't have any points in R1, R2, R3, and R4. So we have S1, S2, S3, and S4 left. And if F is in S1 or S3, then the division would be A, B, and C, D. So EF, AB, and EF, C, D would be convex quadrilaterals. While on the other hand, if it's S2 or S4, then the division would be AD and BC. That is because the angles are again limited by the lines and the different constraints of the convex hull. Okay, so lemma 3.1.4, it's basically the happy ending problem, just to add another line that there is exactly one convex quadrilateral. That is because the converse of angle AED and EDB are both larger than 180 degrees, meaning that these two angles cannot be involved in other convex quadrilaterals. Okay, so the next step, I basically divided the problem into 3-4-2 configurations, a 3-4-2 configuration, a 4-3-1 configuration, and a 3-3-2 configuration. So first, the 3-4-2 configuration. We basically consider this configuration, and by lemma 3.1.2 just now, we can see that we can divide the outer areas into A1, A2, A3, and A4. So since there must be two convex quadrilaterals formed by the middle 2 points and 2 of the outside points on each side, if any point lies in here without loss of generality, A1 or A2, then a convex pentagon would be formed. But if it's in A3 or A4, then we would have 2 points in one of A3 and A4. And if those 2 points form a line that crosses any part of this quadrilateral, then it would violate the original definition of the 3-4-2 configuration, because the 3 point is supposed to form a convex hull. So we would be able to prove that by the limitations of angles again, that the 2 points along with 3 points inside, one of the points inside, 2 of the points on this 4 configuration would be able to form a convex pentagon. Okay, next, the 3-3-2 configuration. So again, we decide the outer area by 3 areas. So if anything is in A2, again, we have a convex pentagon. So if 2 of the points must be in either A1 or A3, and again, by the limitation of the convex hull, we again have a convex pentagon because they cannot cross through any of the any parts of the triangle. And lastly, the 4-3-1 configuration, we divide the outer areas into A1, A2, and A3 like that. So there would be 2 points in one of the areas which would form a convex pentagon again. Okay, so we have proved that S5 equals 9 because the 4-3-1 configuration has 4-3-2 and 4-4-1 configurations in it. The 3-3-2 configuration proves the 3-3-3 configuration, and the 3-4-2 configuration proves itself. And this exhausts all the possibilities. So 4-3-1 and 3-3-2 configuration only has 8 points, but they are suffice to guarantee a convex pentagon. But the other 2 configurations are not, as seen by actual constructions. This one is one of the 3-4-1 counterexamples. And this is a 4-4 counterexample. So we have reestablished the result of F5 equals to 9 using a purely geometric approach, and it will provide an alternative perspective into viewing this combinatorial geometry problem, and perhaps few other cases of the problem geometrically in the future. And we have explored configurations in which the lower bound is not sharp, and it can possibly generalize new aspects of the problem. And these are the references that I used. This is the end of my presentation. Thank you.
Good. Thank you.
Thank you so much.